Imagine you're standing in the lower decks of this massive, like a thousands of tons steel cargo ship, right?
Yeah, miles out in the open ocean.
Exactly. And suddenly the weather takes this violent turn. The unthinkable happens, right? The hull is breached.
The absolute worst case scenario.
Right. You hear that deafening groan of tearing metal and then just the terrifying roar of the ocean rushing in.
It's a terrifying thought.
It really is. So in that precise moment, what actually keeps that massive ship from just plummeting to the bottom of the sea?
Well, most people would probably think it's just, the thickness of the outer hull.
Right, like just a thick steel wall. But the real heroes of maritime survival are actually hidden deep inside the vessel.
Oh, absolutely.
So looking at the stack of sources we have for today's deep dive, specifically, we've got some highly detailed mechanical diagrams and excerpts from a structural manual simply titled Chapter 13, Ship Water Tightness.
Very to the point title.
Very. But it makes it clear that staying afloat is really about this hidden network of highly engineered mechanical barricades.
Yeah, barricades that most passengers or even casual observers would never even notice.
Exactly. So our mission today is to translate these complex, frankly, kind of dry maritime schematics into the physical reality of how you hold back the ocean when disaster strikes.
And the engineering behind it is just incredible.
It really is. Okay, let's unpack this because looking at these diagrams, I'm realizing that the everyday vocabulary we use to describe, keeping water out, it doesn't even come close to cutting it on the open water.
Oh, not at all.
Yeah.
The terminology in maritime engineering is incredibly strict, basically because the physical stakes are so high.
Right.
Like, our sources draw a really sharp distinction between two concepts that, frankly, people use interchangeably all the time.
Weathertight and watertight.
Exactly. I mean, in a normal environment, if your jacket or your watch says waterproof, you just assume water isn't getting in, right?
Yeah, you think, oh, I'm safe in the rain.
Right. But on a cargo ship, applying that kind of casual logic will literally sink you.
Which makes complete sense because, fighting off a rainstorm is very different from fighting off the actual ocean.
Totally different. So the text defines weathertight as meaning that in any sea conditions, water will not penetrate the ship from the outside.
Okay, so that's basically your barrier against the elements.
Yeah, it keeps the heavy sea spray, crashing waves, the rain. It keeps all of that off the decks and out of the upper superstructure.
Like a really sturdy raincoat.
A very sturdy, very industrial raincoat, yeah.
Yeah.
But watertight is a completely different engineering standard entirely.
That's the heavy-duty stuff, like a submarine.
Right, like a submarine. The manual states that a watertight door must prevent the passage of water in both directions.
Oh, both directions.
Yes, and the really critical phrase in the text here is that it has to do this when subjected to a head of water.
A head of water. That basically just means water pressure, right?
Essentially, yes.
But I want to really dig into what that actually feels like physically, because we aren't just talking about a puddle pushing against a door frame here.
Oh, no. We are talking about thousands of pounds of crushing force. You have to remember, a single cubic meter of seawater weighs a metric ton.
Wow. A full metric ton.
Yeah. So if a compartment floods and the water fills up toward the ceiling, the water at the bottom isn't just sitting there peacefully.
Because of all water piled on top of it.
Exactly. It has the weight of all that water above it pressing down, which forces it outward against the walls.
Ah, so that outward force is the head.
That is the head. So a watertight door has to withstand that exponential pressure from either side.
Right.
And it can't let a single drop pass through.
So if a compartment floods, you just seal it off. You basically sacrifice that one section to save the entire rest of the ship.
That's the brutal reality of it, yeah. The watertight doors hold that crushing pressure inside that single compromised room so it doesn't spill over. And what's fascinating here is why that strict compartmentalization is so vital. It's actually not just about the raw weight of the water pulling the ship down.
Oh, really? What else is there?
It's about something called the free surface effect.
The free surface effect. Okay, what is that?
Imagine if thousands of tons of water were just allowed to slosh back and forth across the entire length of a ship as it rolls in the waves.
Oh, man, that's a lot of shifting weight.
A massive amount.
Yeah.
That constantly shifting center of gravity will capsize a vessel incredibly fast.
Which is why the ship's interior is divided up by what the diagrams call bulkheads.
Exactly.
And just to be completely clear for anyone listening, a bulkhead isn't just an interior wall, like, the drywall in your house.
Oh, definitely. Yeah.
It is a massive structural steel partition that spans the entire width of the ship.
Ah.
It slices the whole thing into those isolated sealed compartments.
Right. And history's actually shown us exactly what happens when those bulkheads aren't truly watertight.
You're thinking of the Titanic, right?
I am, yeah. Its bulkheads didn't go all the way up to seal at the top. They were open at the very top decks.
So when the front compartments flooded, the ship tilted forward.
And the water simply spilled over the top of the bulkheads into the next compartment, and then the next, and the next, like an ice cube tray spilling over.
Oh, wow. That's a terrifying mental image.
It is. And the engineering we see in Chapter 13 is basically the modern answer to those historic failures.
Okay, so the concept makes total sense. Divide the ship, seal the flood area, and stop the water from shifting around.
Right.
But obviously, we still need to actually move through these bulkheads during normal day-to-day operations. Like, the crew needs doors.
They do, yeah.
And honestly, getting a piece of metal with hinges on it to hold back the literal crushing pressure of the ocean seems physically impossible to me.
It sounds like a contradiction, doesn't it?
Totally. So I want to pull up this first visual source we have. It's a schematic of a manual lever door. The text calls this a lever watertight door, and it's operated by hand using one or more levers.
Right, so let's look really closely at the mechanics of it in the diagram.
Okay, I'm looking.
You see a standard-looking rectangular door, but it's heavily reinforced.
Yeah, lots of metal.
And it has hinges on one side and then the series of clips all around the edge.
Wait, I need to challenge the basic premise of this design right off the bat.
Okay, go for it.
Because I'm looking at this drawing. If I have a steel door pressing against a steel frame, and there is literally a metric ton of water pressure pushing against it, metal against metal isn't perfectly flat.
You're absolutely right, it's not.
Right, like if you put steel under a microscope, it looks like a jagged mountain range. Water under extreme pressure is going to easily force its way through those microscopic valleys between the door and the frame.
Oh, metal and metal would absolutely fail. It wouldn't even be close to watertight.
Okay, so how do they solve that?
Well, to see how they fix it, you have to look at the cross-section that's labeled detail of door clip in the schematic.
Let me find that. Oh, okay, I see it.
See what's between the actual door and the structural bulkhead. The diagram calls the bulkhead the house side.
Yeah, there's like a little channel there containing a thick rubber gasket.
Exactly. A rubber gasket.
Even with a gasket, though, I have to wonder about the durability here. I mean, we are talking about a harsh marine environment,
Very harsh.
salt water, constantly fluctuating temperatures, heavy industrial use. Doesn't rubber just, I don't know, degrade, crack, and fail exactly when you need it most to hold back a flood?
Oh, that is a massive, massive concern in maritime maintenance, which is why these aren't made of your standard natural rubber.
Okay, what are they made of?
They use highly specialized marine-grade synthetic elastomers, things like neoprene or nitrile.
Oh, okay.
Yeah, they are formulated specifically to resist saltwater, oil, and extreme mechanical wear.
That makes more sense.
But, the gasket material alone isn't enough. It's actually about how the door interacts with that gasket.
How it squishes it.
Exactly. Notice the mechanics of the clip itself on the diagram. There are 6 of these clips distributed evenly around the entire perimeter of the door.
I see them. They kind of look like heavy metal handles.
Right. So when a crew member turns that lever by hand, the clip doesn't just slide behind the frame like, a deadbolt on your front door.
It doesn't.
No. The diagram shows the clip catching onto a wedge-shaped piece of steel on the house side.
A wedge. Okay.
Right. So as you force the lever down along that wedge, it creates mechanical advantage. It physically pulls the door inward, pulling it super tight against the frame.
Oh, I get it. It aggressively compresses that synthetic gasket.
Precisely.
Think about that. You know those really heavy-duty Yeti coolers you might take camping?
Oh, yeah, sure.
Or like a kitchen pressure cooker.
That's a great comparison.
Yeah, because you don't just gently close the lid on those. You have to pull down those heavy clasp-blocking levers. And you can physically feel the resistance as you force the rubber seal to compress.
Right, you have to really muscle it.
Exactly. And that compression is what makes the cooler completely airtight. This ship door is just a massive, heavy-duty industrial version of that exact same mechanical principle.
The physical mechanism is completely identical.
Wow.
Yeah, that state of intense mechanical compression forces the elastomer to completely fill all those microscopic mountain ranges in the metal that you mentioned earlier.
It fills in all the gaps.
Every single one.
Yeah.
That is what forms the impenetrable seal. And, oh, you see those flat stiffeners?
The ones crisscrossing the door in like a star pattern on the schematic.
Yeah, those. They are totally vital to this entire process.
Why is that? Because if the water pressure pushes against the center of the door, the steel might bow inward.
Exactly. And if the door bows in the middle, what happens to the edges?
The edges would pull away from the frame, breaking that beautiful compressed seal we just made.
Exactly that. The stiffeners keep the geometry rigid so the seal stays perfect.
It's just a brilliant combination of simple geometry, synthetic polymers, and human leverage.
It really is.
But okay, let's talk about the reality of using human leverage for a second.
Sure.
Imagine trying to actually wrestle a heavy, swinging steel door shut when the ship is pitching 30 degrees to the side, the deck is soaking wet, and you're fighting literal gravity.
It's incredibly difficult. Human muscle definitely has its limits.
Right.
And ship architecture requires much larger openings than these standard little doorways.
Like for moving cargo around?
Yeah, cargo, massive engines, or heavy equipment. You need these huge corridors between compartments.
And you can't exactly just put a 20-foot tall, multi-ton hinged door on a ship and expect a human to muscle it shut.
Definitely not against the roll of the ocean. The physics of a swinging hinge simply fail at that massive scale.
Here's where it gets really interesting, because when human muscle and swinging hinges aren't enough, you need a totally different mechanical approach.
You do.
The sources introduce a second system here, the sliding watertight door.
Yes, a totally different beast.
Looking at the schematic and the incredible real-life photograph provided of it's labeled door number 9, this thing is massive.
Huge.
First of all, it slides horizontally along a track rather than swinging outward on a hinge.
Right, and sliding horizontally is crucial here. It means the immense weight of the door is entirely supported by the track and the ship's structure.
Ah, so it's not hanging off a hinge trying to fight gravity as the ship rolls.
Exactly. It just slides. And that horizontal sliding action is driven by a completely different source of power.
The text explicitly defines this as using a, quote, hydraulic oil system for opening and closing.
Yeah, hydraulics.
Let's pause and actually explain the mechanics of that, because the schematic shows this massive rectangular steel barrier, and running across the bottom half is this thick horizontal arm.
The door operating hydraulic cylinder.
Right, that's what it's labeled. So how does a cylinder full of oil actually generate enough force to slice a multi-ton steel wall through a rushing flood of water?
It all comes down to fluid dynamics, specifically the incompressibility of liquids.
Okay, break that down for me.
Think about it like this. If you have a closed pipe full of air and you push on a piston at one end, the air just squishes, right?
Yeah, it depresses.
Right. But if that pipe is full of hydraulic oil, the liquid cannot be compressed at all.
Oh, interesting.
So if you push on one end, that exact same volume of fluid must push outward on the other end.
It has nowhere else to go.
Exactly. So tracing the lines on the schematic,
Yeah, I see pipes running from that horizontal cylinder up to a control valve.
and then from the valve, they run all the way up to a central power unit.
And that power unit has a motorized pump in it.
Right. And that motorized pump takes advantage of area and pressure. If a small pump pushes oil into a really large cylinder, it acts kind of like the gears on a bicycle.
Oh, okay. How so?
It trades distance for immense force. The pump just relentlessly forces the incompressible oil into the cylinder, extending the thick steel rod connected to the door.
Wow.
Yeah, and that generates thousands of pounds of linear pushing force, just driving that massive steel panel horizontally across the corridor to completely seal the compartment.
Looking at the photograph of door number 9, you really realize the sheer scale we are dealing with.
It's intimidating.
It looks like the vault door of a bank, painted pristine white, just sliding right out of the bulkhead.
It does.
And during a catastrophic event, a ship might take on water incredibly fast. So the crew needs to be able to hit a button on the bridge and have these massive barriers slide shut swiftly and with literally unstoppable force.
And if we connect this to the bigger picture, they need to do it simultaneously across the entire ship before the water can spread to the next compartment.
Right.
The hydraulic assistance is literally the only thing that makes a rapid ship-wide lockdown physically possible.
Okay, I'm looking at this interconnected hydraulic system, though, and I have a major problem with it.
What's that?
Well, we just established that watertight doors are the ultimate safety barrier needed specifically during a catastrophic accident, right? Like a collision, a grounding, an explosion in the engine room.
Yes, absolutely.
Well, what is the very first thing that usually fails during a catastrophic maritime accident?
The power grid.
The power grid.
Yeah.
If this massive sliding door relies on an electrical power unit to run the hydraulic pump and the ship's generators go dark, doesn't this multi-ton steel vault suddenly just become a giant paperweight?
That's a very fair question.
Like it's just stuck permanently open while the ship fills with water.
Well, that is the exact nightmare scenario maritime engineers have to design for.
Okay, so how do they solve it?
The entire philosophy of ship safety is that you never, ever rely on a single system without a localized backup.
Never.
Never. So when you look closely at both the schematic and the real-life photograph, you'll actually see the fail-safes built directly into the hardware.
Okay, let me look at the bottom right corner of the schematic. Ah, okay, there it is.
You see it.
Connected directly into the hydraulic lines, totally bypassing the main power unit, is a little box labeled hand pump.
Yes. Even if the ship loses total electrical power and the centralized hydraulic system is completely dead, the ship isn't doomed.
Wow.
You can clearly see this in the photograph of door number 9, too. Right next to the door, bolted to the wall of the corridor, there is this apparatus with metal pipes, a pressure gauge, and a very prominent metal handle sticking out of it.
And the source labels this the emergency operation handle and pump.
Exactly.
Wait, so you're telling me that in a pitch-black corridor with alarms blaring and the ocean rushing in, a single crew member can run up to a 3-ton steel sliding door, grab that lever, and manually pump enough fluid to move the door shut?
But it can.
That's insane!
It is, but it works because of that exact same fluid mechanics principle we just discussed.
The bicycle gear analogy again?
Exactly, just in reverse.
Mm-hmm.
The human is operating a very small internal piston, so they will have to pump that handle frantically, maybe 50 times, just to move the massive door a few inches.
Oh my.
Yeah, they're trading a huge amount of physical movement for the immense force needed to push the oil into the main cylinder.
It takes incredible physical exertion.
A massive amount.
Yeah.
But the mechanical capability is hardwired right there at the point of danger.
That is wild. It's just a completely localized, self-contained hydraulic backup that essentially runs entirely on human panic and adrenaline.
That's a very accurate way to put it, yeah.
The source photo also points out another label here, local operation and handle. And that one is right next to the hydraulic cylinder on the door itself.
Right, and that ensures the door can be controlled mechanically right on the spot.
Bypassing the remote electronic controls on the bridge.
Exactly, because those electronic controls or wires might have been severed or short-circuited by the initial damage.
That makes sense. Looking back at the schematic of the sliding door, there are a couple of other crucial safety details that really highlight the reality of this intense environment.
What caught your eye?
Right above the doorway, there's a label for an alarm.
Ah, yes. Think about the physical danger of the door itself.
Yeah, we just established the immense hydraulic force required to slice this steel wall through rushing water or against the tilt of a sinking ship.
Exactly.
Mm.
If a centralized command from the bridge suddenly triggers all the watertight doors to close at once, it becomes a massive crushing hazard for the crew.
Right, because an automated hydraulic cylinder pushing with thousands of pounds of force is not going to politely stop if someone's arm or leg is in the way.
It absolutely will not bounce back.
It's not an elevator door.
No, it will crush whatever is in its path.
Yeah.
And remember, the environment down in the lower decks is incredibly loud, engines roaring, metal shifting.
So you need an unmistakable ear-piercing auditory and visual warning.
Precisely. The alarm guarantees anyone in that corridor knows the massive steel guillotine next to them is about to slide shut.
Wow, a steel guillotine. That's a vivid way to put it. There's also an isolating switch noted on the schematic over on the left side of the bulkhead.
Which speaks to that localized control again.
So if a crew member is trapped, or the system somehow malfunctions, they can manually cut the hydraulic pressure right there at the door to stop it.
Yes, they can stop the door locally. It is just layer upon layer of redundancy.
And that layered approach is really the true architectural genius hidden in these documents, isn't it?
It really is. We start with the weather-tight perimeter, keeping the ocean out under normal, if rough, conditions.
The raincoat.
Right. Then internally, we construct a maze of heavy steel bulkheads capable of withstanding the literal crushing pressure of the sea and preventing that deadly free surface effect.
And we use those manual lever doors with marine-grade compressed rubber gaskets for standard access.
Exactly, ensuring a perfect seal through just simple, reliable mechanical advantage. The wedges and clips.
And then for the massive cargo corridors, we escalate to the hydraulic sliding beasts.
Wielding tons of liquid force to lock down the ship in seconds.
But even then, even with all that power, we layer on manual fail-safes, emergency hand pumps, local operation handles, and isolating switches.
Because it is an entire philosophy of resilient design. It assumes the absolute worst will happen.
A breach, a total loss of power, a flooded compartment.
All of it. And it provides a physical mechanical answer for it. The combination of weather-tight external boundaries and highly regulated, watertight internal compartments is exactly what transforms a hollow metal hull into a truly survivable structure.
So, what does this all mean for you, listening to this deep dive?
That's a lot to take in.
It is, but I think it fundamentally shifts how we should view these massive floating cities. Keeping a cargo ship afloat in the middle of a violent ocean isn't magic.
No magic involved.
It's not just about having a thick outer shell either. It's a combination of deeply considered physics and engineering.
Absolutely.
It scales all the way from the microscopic compression of a synthetic rubber gasket by a hand-turned wedge, all the way up to the complex fluid dynamics of massive redundant hydraulic cylinders.
Every single detail, every single pipe and valve is designed to combat the relentless, crushing reality of that head of water.
It really highlights a fascinating intersection between cutting-edge automated engineering and fundamental human reliance.
It does, because we can build the most complex, forceful hydraulic systems in the world, capable of moving tons of steel at the push of a button from a comfortable air-conditioned bridge.
Right.
But the marine engineers who design them understand the chaotic, completely unpredictable reality of the sea better than anyone.
Which brings up a final provocative thought to leave you with today. Think about all the sources we examine in this deep dive.
From the simple lever door up to the hydraulic.
Exactly. From that basic swinging door all the way up to the incredibly advanced hydraulic system of sliding door number 9. Every single one of these highly engineered systems features a manual hand pump or a physical lever as its absolute final backup.
It's a great point.
It's a stark, almost humbling reminder. In the most technologically advanced, heavily automated environments we can construct, ultimate survival often still comes down to basic human muscle, sheer physical willpower, and grabbing a lever when the alarm bell finally rings. The ship might be built of structural steel and incompressible fluids, but it still requires the human hand to save it from the depths.